first. Hello and welcome to the Ethereum Engineering Group meetup. I'm Peter Robinson, and today Stan Kladko from SKALE is going to give us a talk on SKALE. So Stan, why don't you introduce yourself before you share your slides?
Yeah, so my story is actually very simple. I think I'm a very typical nerd. When I was like a school boy, I studied mathematics, physics. I participated in all kinds of competitions in math and physics. And then I did a master's degree in physics in Kharkiv in Ukraine. And then I moved to Germany. And then I did my PhD also in physics in Germany. From Germany, I moved to Los Alamos National Lab in New Mexico, in the United States. I again was doing physics. Then I moved to Stanford University in Palo Alto in the States, and I kept on doing physics. My boss there was a Nobel Prize winner. He got a Nobel Prize for quantum Hall effect. So it was really like hardcore physics. And then I kind of realized that at the time, I think I realized that computer science was more interesting because especially at the time I moved to Silicon Valley, there were so many startups. So I moved to startups. My first startup was called Ingram Networks. It was founded by Professor Bonnet. He's pretty well-known cryptographer at Stanford University. So the startup was doing a hardware crypto encryption box, essentially, something that you can put on a network and it would just encrypt all of your databases. And then from this one, I moved to a security lab. So I was running a security lab, which was doing security assessments for the US government, for the National Institute of Standards and Technology in Maryland. And from that one, I had a startup which was doing Wi-Fi security, and another one which was doing big data. And the big data one didn't really go well. So we tried competing with Google, and we were just about to essentially acquire or close the company. And then suddenly the Ethereum thing appeared, and our investors pretty much told us that, guys, instead of shutting down your startup, just go and maybe you can do something for blockchain. So I literally flew it was in 2017, I flew to DEFCON 3, which was in Cancun in Mexico. And I think the moment I entered like this conference, I really liked it. And I realized it's a very new thing. So we kind of tried to find a problem to address, and a very kind of simple problem was to understand how to solve scalability, so how to run fast blockchains. So that's pretty much how I got into this field. And for the last 3 years, we've been trying to understand this consensus, how to do blockchain, how to run it fast, how to do proof of stake consensus. And mine pretty much like entire talk is going to be about this. And the only thing I just want to say is that it wasn't something that we immediately found. We tried different iterations, and ultimately we came up with a scheme which explains, I think, consensus in simple terms and provides more or less nice framework for brain, for understanding. So my talk is going to be about this framework, how you can understand proof of stake consensus.
That sounds great, and what a very interesting history you've got. So please present your slides.
Okay, well, let me start. Let me share my screen. Okay. Okay. So I hope you all see my screen. Let me move this somewhere.
Yep, we can see it.
Okay. Okay, I'll move this somewhere. Maybe this way. Okay. So as I just told you guys, we've been trying to understand how consensus works. Pretty much, it's a very kind of simple sounding problem. You have some number of computers, servers, and these servers run blockchain. And pretty much there are two ways. One is the Satoshi Nakamoto way, when you do proof of work, lots of number crunching. But then there's another way which is called proof of stake, where essentially you don't have number crunching, and you're trying to replace security of number crunching by security, essentially by crypto, by some mathematical crypto algorithms. Turns out that it's possible to do it in a provable way, and I'm going to talk about this. I just want to start with saying that it was an interesting situation in 2017 when we started kind of thinking about the consensus and doing things. My co-founder Jack, who is like he's a business guy, he asked me how can I like understand it in a simple way. And at the moment I realized I couldn't explain it in a simple way. So for the last 3 years, the journey for me personally was trying to understand consensus in general in a simple way. And after like essentially 3 years of iterations, I think we now have a framework, something which we kind of backronym standard kit for asynchronous ledgers. It's a framework that actually allows you to create all kinds of different consensuses, proof of stake. And also it's a framework which allows you to find weaknesses in existing consensuses. Pretty much any proof of stake consensus you can actually explain using this framework. So let me start talking about this. One thing which I want to mention from the beginning is that probably one single talk is not enough. In the perfect world, there would probably be 5 or 6 talks. So what I'm trying to do is, instead of covering every single topic, I'm just gonna give you a feeling, and I have some problems inside these slides. So if you guys want to understand things better, you can actually later try solving the problems or try thinking about this. Because one of the important things about consensus is that it requires you to change your thinking, because it's a distributed system. So things happen in a little weird way. It's a little bit of a weird mathematics, I would say. Okay, so let's talk about the provably secure blockchain. Why do we want the blockchain to be provably secure? Well, it's money pretty much. People put money on blockchain, and the beauty of Satoshi Nakamoto's algorithm was that it's simple and it's probably secure. So, and for whatever reason, really strange reason, I think Bitcoin and Ethereum, they run, and they haven't been hacked, which is a pretty huge accomplishment, I think. So you want to have something, when you replace proof of work with proof of stake, you want something probably secure, because it's money. A single byte change could actually, lead to catastrophic consequences. So you need an algorithm where you can prove how it works and how is it secure. So first of all, the actual problem is really simple. You have a number of computers in the network, and you essentially have stages. The first stage is people submit transactions to the stage, to something which is called a pending queue. And there are different ways to implement a pending queue, but in general, you can see a pending queue as something like transactions. They're disordered, they're somewhere. Probably like every node in your network has to have almost the same transactions, although you could have things like a latency in your network. So transactions, the pending queue on every node does not have to be exactly the same, but it's approximately the same. Then you have a ledger service, and ledger service is something which takes the transactions here and actually orders them into a chain. And it seems to be a pretty simple problem, but what you need to do is that the chain, the copy has to be exactly the same on every node, on every server in your network. Now, every server has different latencies. So on some servers, your blockchain may grow fast. On some other servers, there may be a delay, but the parts of the blockchain that overlap, they have to be identical. So the entire purpose of the ledger servers is to create ultimately identical chain on each node. And then, so this is actually the most complex thing. How do you do this ledger servers? That's the most complicated thing in the system. And then ultimately, once you have the chain, the virtual machine eats transactions. So you can see a virtual machine as a bot, as some kind of a entity which moves on the chain and processes transaction one after another. And when it eats each transaction, it changes its state. So if you have an ERC20 token, a transaction may change balances. You change who owns what. So the virtual machine, you can see it as this guy who moves, and then on eating every transaction, changes the state. On this picture, yellow transactions have been eaten already, and white ones haven't been eaten. And that's pretty much the story about the virtual machine. Actually, the virtual machine is really simple to implement, and it uses simple algorithms compared to the ledger service. So the ledger service is the thing which is the hardest to do in a mathematically clean way. As I already mentioned, the ledger has to be only eventually consistent. And eventually consistent means that different nodes have different latency. And in this picture, for instance, this guy, node number 3, is kind of slow, so it only has 2 blocks. And this guy, node number 4, is fast, it has 4 blocks. But at some moment in time, node 3 will also get these other 2 blocks. This is something which is called liveliness, meaning that the blockchain will keep growing on each node. And once this guy, node 3, gets the remaining two blocks, the 4 blocks on both nodes are going to be the same. So the eventually consistent means exactly that. There is a different speed, but the pieces which overlap, they are exactly the same. That's a huge principle that you need to always achieve in your blockchain. So now I have some interesting, for people who want to go a little deeper into blockchain and into this thing that we just discussed, I have 2 problems. One problem is easy, and just can think and answer a question. Why do we need to use blocks at all, right? In this picture, we order transactions in blocks. In theory, there could be no blocks. You could just add one transaction after another. So that's problem number 1. This one is kind of easy. And the second one is problem number 2. This is for people who understand Ethereum in particular. So on this picture, we said that ledger service could be completely independent from the virtual machine. They look like 2 different, completely independent things, but there is actually one point at which ledger service needs to get information from the virtual machine. And if you are deep into the Ethereum, you can answer this question. Now, how do we understand? Now we're going to talk about the ledger, about the consensus, because that's really the most non-trivial part. And the question is, because this is pretty complex, how can we understand it? And usually the way to understand a complex thing is to be able to split this into logically sequential parts or logically distinct parts. This is just an example. For you guys, for those who understand, who know about compilers, a compiler is a pretty complex thing. If you have a compiler for C++ or for Java or for some other language, it's pretty complex and actually a very advanced thing. But we understand compilers by splitting them into phases. So if you ever taken a course on compilers, you know that the compiler has the 7 phases. And now if you have this framework, you can modify each phase and study it, and things becomes much simpler just because you split this into phases. So that's actually a general principle. If you have a complex system, you want to understand it, you split it into like smaller things, and now it becomes easier to understand. So my point here is that for consensus, we also need something like that, something that we have for compilers, being able to split consensus into logically different phases and then agree on those phases. And if we can do it, then we will understand this thing better. So after pretty much 3 years of work at SKALE, we came up with this model of consensus that actually helps us to understand it better. So let me just first try to move this somewhere. Okay, I'll move you guys here. Okay. Okay, maybe I move it here. Okay, so we came up with this model which helps people understand things better, and it actually has 5 stages. That's kind of the most important slide for this talk. And if you don't remember anything, will not remember anything else from this talk, this is the kind of the best slide for you to concentrate. So consensus, the ledger or consensus or blockchain consensus or proof of stake, wherever, whichever way you name it, could actually be split into 5 phases. And these 5 phases you can find pretty much in any consensus. You could take Tendermint, you can take the thing that Facebook is doing or whatever, and you'll find, or you can take, for instance, EOS, and you'll find all of those phases. In some cases, you'll find the phases that are mixed together. In some cases, like for EOS, you will find insecure places or phases that are missing. But this framework allows actually to utilize pretty much any proof of stake consensus, and it has 5 steps. First step is a pending queue. Before ordering transactions, you need to have an approximately consistent pending queue on each of your nodes. People call servers nodes in the blockchain speak. So you need to have a pending queue, which is approximately consistent on all of your nodes. It doesn't have to be exactly consistent. And usually the way this pending queue is done is doing some type of a gossip or broadcast. You somehow need to get transactions to your nodes, and the pending queue on each node has to be looking similar. Then once each node has the pending queue, the second step of pretty much any consensus is block proposal. You can have one node proposing a block. You could have multiple nodes proposing a block, but at least one proposal needs to be made, or several proposals need to be made. And here there is a very important thing which immediately comes. The proposal has to be data available and unique. And these 2 things are super, super important. Data available means that the entity, the node that distributes proposals needs to make the proposals widely available on the network, because otherwise there is a very simple trick for a malicious node to essentially stop the blockchain. A malicious node can pretend to propose, but then once this proposal is selected, the malicious node can withhold the proposal from some of the nodes. So which means that when you do a proposal, you need to prove that you actually distributed it widely on the network, because if you didn't, you could later use this to halt the blockchain. So anyone who proposes needs to distribute it, or in more mathematical way to make it data available. And we'll talk later how you can do it. But basically the trick is that you need to at least make your proposal available to at least one honest node. And then, because then the honest guy can actually send the proposal to all other guys. In this entire system, there are nodes which are supposed to be honest, and the guys which are supposed to be malicious. And in most of the models that I'm going to be talking about, you're supposed to have no more than 1/3 of bad guys and 2/3 of the good guys. So that's about data availability. Now, another important thing is uniqueness. When you propose, you need to make sure your proposal is unique. This means otherwise there could be again a hack, a trick to kill the blockchain. And the trick would be just to have some nodes accept proposal 1 and some nodes accept proposal 2, and then the blockchain would diverge. Again, it's a super important principle. A malicious proposer could make some of the nodes accept proposal 1 and some of them accept proposal 2 by essentially making 2 proposals, make it not non-unique, and that would kill the blockchain. So these 2 principles, data availability and uniqueness, are super important to enforce at the proposal stage. If you don't do this, then the blockchain is vulnerable. There's a security problem. So then the third phase is that once one node or many nodes, made proposals, you need to decide on which proposal wins. Sometimes actually you may decide that no one made a proposal because the bad guy could actually withhold from making proposal. So the outcome of consensus could actually be that there's no winning proposal. Is essentially no one won. But anyway, the stage 3 has to be decided. There has to be a consensus, and the consensus means that every single node on the network needs to decide on which proposal won. So if Alice decided that proposal 5 won, then Bob needs to decide the same. And this is, again, super important because if different nodes decide on different proposals, the blockchain will diverge and essentially die. Anytime the chains diverge, the blockchain is killed because the entire purpose of blockchain is to have identical chains on every node. This third stage is selection. Essentially, you have proposals, you select which one won. Now, the fourth proposal is that you need to somehow have a decision proof, because historically, if someone else later downloads the blockchain, someone needs to be able to prove that that's the correct replica. So you need to do some kind of a proof for the future which decision was made in step 3. And usually this proof is done by some kind of a signature. This is actually quite simple. Essentially, you need to somehow sign the winning proposal just for the future, to make sure that the proposal, that in the future you can prove that that was the winning proposal. And then once you have step 4, essentially you have a committed block. Committed block means that your proposal has been selected, it's available, it's committed, and now everyone can process the proposal. And then we can have the EVM running or whatever other virtual machine, and things become really, really, really simple. So these 5 phases, pretty much any consensus you have to have these 5 phases. And if you understand these 5 phases, it's going to help you a lot, because many people don't understand this, and even many consensuses don't understand this. If you try, for instance, analyzing EOS, you will understand that they don't understand how things work. So they made a huge number of mistakes in their consensus by just even not understanding these very simple principles. Okay, so I'm just gonna again go over these principles again, because this is kind of the major part of this talk. If you at the end of this talk understand the principles, that's gonna be a huge progress. So what pretty much any blockchain consensus needs to do, if it's probably secure, first you have to distribute transactions reasonably well to pending queues. On each node, they don't have to be perfect, but looking pretty much the same. That's the starting point for consensus. The second thing is that you need to have one or many nodes propose candidate blocks. And during this second stage, you need to enforce mathematically uniqueness. Every proposer can only propose a single block, and wide distribution. Wide distribution means that every proposer needs to at least distribute to one honest guy, By the way, if you have 2/3 of honest guys and 1/3 of bad guys, if you distribute to 1/3 plus 1, you are guaranteed to distribute to at least one honest guy, because there are not so many bad guys. So actually distributing to lots of nodes actually guarantees data availability. So that's really important. And then again, step 3, you decide which proposal wins, or sometimes you can decide that no proposal won. One simple example of that is a malicious proposer could just withhold proposing anything, and the nodes just need to come up to a decision that no one proposed, right? And this is called the default block. A default block is an empty block, but not just an empty block which is proposed by someone. It's a block which is created as a result of someone non-proposing. So this default block is really nice. Is a really nice abstraction. Then once you decided which proposal won, you just need to sign it in some way. This is kind of an easy part. And then the last phase, when you have a committed proposal, a particular node, let's say a particular node knows that proposal number 5 won. At that moment, this node may actually, it sounds a little bit strange, but at this moment, you can have situations where a node knows that proposal number 5 won, but this node it does not yet have the proposal. So there are some cases, I'm going to talk about this later, when a node knows a particular proposal won, but it doesn't have the proposal, so it actually goes and downloads this proposal from some of the other guys. And this is called finalization. That's the thing that you unfortunately need to do because the system is distributed and has latencies and also kind of strange things. Okay, so that's really the framework. And when you start thinking in terms of the things, unfortunately, you need to kind of change your brain a little bit. So it forces your brain to be changed. So sometimes, initially, I think it's hard to think. But then once you think about this for a longer time, you start kind of getting into this distributed system thing, and then it becomes easier. But it does require some brain, I would say, changing your brain a little bit. Okay, so again, talking about the same thing again. So you have the approximate pending queue, you need to have data available unique block proposal, you need to have a consensus, you need to have evidence generation, usually a signature, and then you need to have a committed block download. You have this, if you don't have a block at the end, you download it. So if you have these 5 things, now the great thing is that if you can prove, if you use provably secure algorithms for all of the 5 phases, it's a very simple, you can have a very simple proof that the entire thing is secure. So you have a complex system, you need to prove its security. If you split the system into pieces and you prove security of each piece, then kind of you can magically prove the security of the entire thing. So in this way, if you stay within this framework, you can actually prove security. And by changing things, you can change things on each phase, on each step. You can just actually, you can generate a family of consensuses. It's not a single proof of stake consensus, it's a family, because on each stage you can use different algorithm. And if the algorithm on each stage is provably secure, you're staying in the provably secure world. Okay, so then again, the really important concept to understand is that what is Byzantine fault tolerance and liveliness? What does the thing means? It means that you have a system, you have like n nodes. In Scale, for instance, by default, we have 16 nodes. And you prove that the system operates correctly if, say, 5 of 16 nodes are hacked. And operating correctly means really simple for blockchain. It means that the chains are the same, identically the same on each node. It's trivial, but it's actually not so easy to achieve. So correctness means that you have 16 nodes, 5 of them are hacked. The hackers do whatever they want, but the remaining 11 nodes are consistent. The blockchains look the same. So that's the correctness. And liveliness means that the blockchain actually proceeds. The blocks are being literally generated. It doesn't stop. You know, you have continuous generation of blocks, and these 5 guys clearly trying to do whatever bad, including just not doing anything. Sometimes not doing anything is really bad. But whatever these 5 guys do, the remaining 11 guys don't care, and the blockchain proceeds. So this is the kind of the holy grail of Byzantine fault tolerance and liveliness. So here are some fun problems, really like going really fast about them. You know, but problem number 2 shows that having a hacked node is equivalent to a very buggy node. It's like, you know, you guys probably know the story about a monkey. If a monkey prints like types randomly for a long time. At some point, the monkey will, create Shakespeare's work just by randomness. So actually having a hacked node is equivalent, to a very buggy node, in the sense that a buggy node can do really, really bad things. And just think about a really, really super trivial protocol with a single master node. Let's say you would say, okay, node 1 is a master. It's a primary node, and only node 1 makes blocks, and all other nodes just download blocks from node 1. Show that this blockchain is not consistent and not live, is not correct. So even if there's one secretly malicious node, this is not correct. Yeah. And then the problem number 4 is pretty complex, advanced. I actually don't know how to solve it in an easy way, but it's known that for 2 nodes, there's no way to create a blockchain which is consistent and live. So if you want to have a complex problem, here's problem number 4. Okay, now I'm going to really briefly, in a fast way, so I think I covered pretty much the most important thing. I'm going to really brief way talk about mathematics. So there are really interesting mathematical algorithms involved in doing all kinds of things like this. There's threshold signatures, distributed key generation, distributed random number generation, binary consensus, while pairing elliptic curves, and group theory. It turns out that to do this blockchain thing, the proof of stake, we need all of these really interesting mathematical algorithms, and without any of them, it's really hard to do it. So M of n threshold signatures. It's actually a very simple concept. You have, say, 4 guys, and out of this, and you have kind of 4 keys, and then you create a threshold signature which proves that 3 or 4 guys made the decision. And once the signature is created, it's actually anonymous in the sense you don't know which 3 or 4 can make this decision. So once you have the signature object, what happens is that each like 3 or 4 guys, they sign a piece of information, and these pieces, the signature parts, signature shares, they can be glued into a signature object. And then when you have the gluing, then you have the object which actually tells you that 3 or 4 people signed, but you don't know which 3 or 4. So it kind of looks like a jigsaw. Essentially, you need only 3 out of 4 pieces, and whatever 3 pieces you take, you actually have the same result, the same signature. It's really interesting mathematically. But for these signatures, you need to have initial key generation. The keys actually have to be connected in a particular way. So there's actually an algorithm which to generate keys for this type of signatures. And so what you typically do, you have a ceremony, and the 4 guys generate together keys. And then once the keys are generated, any 3 out of 4 can sign and create this the threshold signature. So that's one piece, the threshold signatures. There are some problems. You will be able to get the slides later. Then it turns out another interesting thing, based on these threshold signatures, you can have another really cool algorithm, which is called distributed random number generation. If you have a group of people, can this group of people derive a common random number, even if some of these people are bad? Let's say you have 4 people, one of them is known to be malicious, you don't know who is malicious. Can this group derive a common random number in such a way that their number is random, and the bad guy cannot influence it? It turns out there's an algorithm to do it, and it's based on the threshold signature. Essentially, the signature itself becomes their number. So threshold signatures lead you to another algorithm, which is called distributed random number generation. People also call this algorithm like a common coin. It's a common coin because people essentially collectively flip a coin. And then finally, kind of the most interesting algorithm that is used is something which is called the binary consensus. It's also called a prisoner problem or Byzantine generals problem. So basically, that's really the cornerstone of the entire proof of stake. And it's so I'm gonna talk about like in 5 minutes about this problem because that's really, really, really important. So that's one way to understand this problem. Let's say you have 4 prisoners in solitary cells. And out of these 4 prisoners, there are 3 thieves. And one of them is a cop. And you don't know who is a cop, who is a thief. No one knows who, right? And each prisoner has a phone to call. You can call any other guy, but you don't know who the guy is. Could be a cop, could be a prisoner. So what each prisoner does, they flip a coin and gets either 1 or 0. They start with a random set. Each one of them has either 1 or 0. And now they have to agree on a consensus value. So ultimately, at the end of the protocol, all prisoners need to say 1 or 0. Each of them starts with 0, 1, but they need to talk and come to a consensus. And then once they get to the consensus, they cannot agree on a number that no one had initially. So if they all had zeros, they cannot agree on 1. If they all had 1s, they cannot agree on 0. So you start with saying either 1 or 0. And then you're supposed to talk. You can call any other guy and talk to the other guy and keep on talking. At the end, you are supposed to get to a consensus, 1 or 0. Everyone has to say the same thing, but the consensus has to be on something that initially at least one guy proposed. If no one initially proposed 0, you shouldn't agree on 0. This is kind of a strange mathematical problem. You can also talk about Byzantine generals attacking a city, and one general says attack from the left, another one says attack from the right. But then at the end, all generals need to agree, but the agreement, again, needs to be on something that at least one general initially proposed. This is kind of a problem which is really strange, and it takes time to understand. Turns out there is a huge connection between this mathematical problem and consensus, essentially in both ways. If you can do a blockchain consensus, you can solve this problem in a super simple way using a smart contract. So on Ethereum, this problem can be solved really easily using a smart contract on Ethereum. And it also turns out the other way is also true. If you can solve a binary consensus, you can build a provably secure blockchain, select blocks pretty much. So there's a two-way connection between the binary consensus and the blockchain. And if any of you want to go deeper into this, you can study this more. But for now, I just want to state that it's really interesting that these two problems are almost equivalent. And now the question is, how do you solve this binary consensus? It turns out there are many algorithms, many, and now even more. And there are different algorithms. The best known solution which was published in 2015. We're actually using this at scale. The best solution uses threshold signatures and has the total complexity is n squared, meaning that each prisoner talks to each of her counterparts just maybe several times, like 3 times. Essentially, when you solve this problem, each prisoner can call each other prisoner, and it ends up having on average like 3 rounds. So if you have 4 prisoners, you will need to call like 12 times essentially. So that's n squared, but it's n squared for the entire team. For any particular person, it's just O over n. Okay, so that's a fun problem set. If suppose these prisoners can run a private ETH blockchain, try designing a Solidity contract that solves binary consensus. That's really fun. The last important thing in this talk is synchronous versus asynchronous network model, and I'm just going to go over it and then maybe just skip the rest of the slides and just take questions from you guys. So there are 2 ways to implement consensus. and two camps, a synchronous camp and asynchronous camp. And you're trying to build a system, a consensus, and nodes interact with the networks. So when you try to prove things, you select the network model. The synchronous model assumes that you always have bounded latency on the network. So always the network delivers messages in time less than 1 second, say. And so if any of this breaks, the mathematics breaks. A synchronous model does not make an assumption on the latency, on the network latency. So the message could be delivered in 1,000 years. So if you prove things under a synchronous model, if let's say a year from now the entire global network is split, the asynchronous consensus will just wait, and after the split is resolved at the global level, asynchronous consensus will just survive, while the synchronous consensus will break totally. So that's one of the reasons why asynchronous algorithm is incredibly better. The second reason is because sometimes you can have good guys crash. Let's say you're running your nodes and you have the majority of your nodes are good guys, but a good guy could just crash and not fulfill the protocol just because of memory leak or whatever, or hard drive is burned. So for asynchronous consensus, because there's no bound on the message delivery, you can restart or crash any node. And if after restart a node comes back to the same state, the asynchronous consensus does not even notice. So the node does not need to be deemed bad because there's no bound on the message delivery. So asynchronous algorithms are incredibly better because they help you to survive crashes and your hard drive burned, while synchronous protocols break completely if these things happen. That's why in the realistic network, at least the conclusion that we came to at SKALE, that in a realistic network, it's much better to prove things under a synchronous model as compared to the synchronous model, because in the asynchronous model, crashes don't actually have you to modify your proof. So that's really important. Problem number 10, let's say you have a synchronous model. Just think about this. Let's say you have a synchronous model, your blockchain is probably secure under assumption that the network always delivers messages, although the delivery may take a long time. Show that a server crash does not affect the network protocol correctness as long as the server continues the protocol at the point where it crashed. So the server crashed, it took 2 hours to fix the server, the server comes back and starts from the same state. Just mentally think about this and understand that in this case, the crash will not affect the network protocol if the model is asynchronous. Okay, so these are the steps again. So I'm gonna skip over the rest of the slides. I'm just gonna talk really fast about data availability. How do you prove that when you propose, you distributed your proposal too widely? You prove it essentially using a threshold signature. Let's say that you are proposing and you know that 2/3 of the guys in your network are good. What you can do, when you propose, each time you propose, you actually collect a piece of the threshold signature. And at the end of the proposal, 2/3 of the guys will accept your proposal because they are good. You collect the pieces and then you get the supermajority threshold signature. And this threshold signature is a proof of the fact that your proposal is widely distributed, because you wouldn't get the threshold signature if you wouldn't distribute to 2/3 of the guys. Okay, so I think that was enough of an introduction. I have much more slides on my my deck, but I think it may be too much for a single talk. So the slides will be shared and you can read the slides. You can also, if you have some questions, you can ask questions on Twitter, or we'll also have a Telegram group at Scale. I can share the group. But I just want to stop at this point and just the last thing I want to say before we can go into questions is that if you want to understand consensus better, you can think about this slides a little more, read them, and this provides a really nice framework to understand how consensus works and makes some of the complicated things simpler. So you could, for instance, a good exercise, you can take Tendermint, which is a pretty good consensus. Tendermint has some weaknesses, but not many of them. And there were people, I think in Spain, there were some researchers in Spain that showed how to fix those weaknesses. But you can take Tendermint and think about all of these principles. You can think about block proposal, you can think about data availability, wide distribution, you can think about uniqueness, just trying to understand how all of this is achieved in Tendermint, which is a good example. And as a bad example, you can take EOS, for instance, and try to understand if they do have data availability or uniqueness, or if they don't have it and just rely on all nodes being honest. That's another example. You can pretty much use this framework to understand many things about existing consensuses. With that, I would like to thank you for your attention. And maybe let's just go into Q&A if you guys have any questions.
Sure. Thank you, Stan. So I know I've got one, but before I fire off, does anyone else have questions?
I think I missed what you said, Peter.
Yeah. So what I said is I'm opening the floor to questions to see if other people have questions before I say anything. Come on, Stefan, I know you're dying to ask a question. So for an asynchronous consensus protocol, if you need, say, 3 of 4 nodes to agree on, say, the next block, and say 2 nodes go down, and but it comes up 1 year later, you're saying, oh well, that's okay, it's good, we're all good because the protocol keeps on going. But if you were hoping to use the transactional output, that's still a bit of a problem because you don't have liveness, kind of. I mean, you don't have the results.
I understand the question, Peter. That's a great question, actually. So, one of the things which complicates things even more, you have a consensus. You can have a blockchain consensus, which is totally secure. The problem is if one of the nodes drops out of the network for a long time, because in your implementation of consensus, you usually have fixed memory and fixed hard drive. If you could keep the entire state of all blocks for everything of the protocol, you could potentially allow anyone to drop out for an infinite amount of time. But because your ability to record things is finite, if someone breaks for short time, it's one thing. If someone breaks out for a long time, what can happen is that other guys may have already lost let's say you dropped out on block 6 and 1 year passed away, and the guys are already working on block number 6 million, right? So you wake up and you say, okay, I still don't have block number 6. And the guys, they could have kept the entire state of the protocol mathematically, and they could help you to like proceed with block number 7 and 8, but they just actually had to throw away the state just because they have limited capacity on hard drive or RAM. So in addition to mathematical proof, you have the problem that at some point you need to start dropping the state, but usually, and there's a way to fix this problem, you add another mechanism, essentially catch up. Essentially, if you drop out of the system for 5 minutes, when you come back, the other guys they still have the state, they didn't drop the state corresponding to the protocol, and you just continue the protocol. You just look to the network as a really, really slow guy, but the protocol just continues. But if you drop out for a year, you come back and there's no state which corresponds to your block number. What you do, there's a mechanism which is called a catch up. Essentially, there's a history of blocks kept on other guys, and each block is signed using a threshold signature. So what you do, instead of participating honestly in the consensus, you just take the other guys and you download the historic blocks from them, and you actually verify the threshold signature. So using this catch-up mechanism, I think many consensuses do have this. We do have it at Scale. I think Solana has it too. I've seen them just using the word catch-up. So catch-up means that if you lost your state, the last resort is just download blocks, historic blocks, and check the threshold signatures. Losing the state is the most complex thing to address, and if you could keep the entire state always, that would be much better. We at Scale, we take extreme precautions not to lose the state, and one of really important things in order not to lose the state is when you want to switch the node off. Let's say you want to change the hard drive. You need to switch the node off, right? And then change the hard drive and you bring it back, which is usually okay because we have, like, say, at Scale, we have 16 nodes. And out of the 16, we allow 5 to be hacked, including just being powered off. So you can take a Scale consensus and power off out of the 16 nodes, you can power off 5. It won't even notice it. So you can repair 5 at the same time. But what's important is that when you switch the node off, the best time to switch off is at the block boundary, when the node produced already block number, say 7, and did nothing for the block 8. That's the best time to switch the node off. Because if you switch, if you crash in the middle of a block production of a protocol, you lose the state, you lose the variables corresponding to the protocol, and then you are in an inconsistent state. And then you can't participate when you are up in this particular protocol. You could, and we tried doing this at Scale, you could have a totally persistent protocol where every variable always is stored on the hard drive. Essentially, every variable is stored in level DB. You don't store anything in RAM. But unfortunately, it becomes impractical. Things become incredibly slow. So you could have a super secure protocol where you don't store anything in RAM. Everything is stored on the hard drive. Every byte immediately, every state of the state goes to the hard drive, and then you could do, like, you could switch it off at any time. It's on the hard drive anyway, and you switch it on, and you have a perfect protocol, but it becomes really slow. So you have to do this trade-off, and the trade-off you make, it's safe to switch things off at the block boundary. And if you crash in the middle of block production, you can't participate in this block production when you're up. You need to wait out and participate in the because what you could do, really a very simple bad thing to do, would be for you to say something in a consensus and then crash, and then when you wake up, you forgot that you said something and you say a different thing, and you become essentially malicious. So these are the things. And so I think the probably secure thing is a simple thing. Incredibly hard thing is to deal with state, with crashes and losing the state. And I think there is no, unfortunately, there is no magic button in this. So pretty much any blockchain, because of crashes, there's always a possibility to lose a state, which means that unfortunately it's really hard to produce a blockchain which is 100% secure and consistent because of the crashes. But you can do a pretty good job, I think. So, but that's really a super important question. That's where the hardest thing comes from.
And so if in your protocol, though, you would have, the node would then wait for the next round, so the next block production. Okay,
Totally.
well, I mean, that's still not too bad. Yeah.
Not too bad. I agree. It's. I think, you know, the good thing about having things mathematically proven is that you at least understand where the problems are. So at scale, actually, at this moment, the protocol that we have is pretty stable, and we have very small bug fixes because we have a mathematical model. And we know, for the beauty of mathematics is that if you've proven something, the only thing you could have is you didn't implement the code correctly. So it could be a human error or bug, but you have always something to compare with, the mathematics. And I think that it's also the beauty of Nakamoto consensus, because it's mathematically very clean. People, some of the protocols, people tried like doing really fast protocols, and they went the way of not actually having mathematics, but just they keep on patching things. So if they have a problem, they have a patch, and they have a patch on the patch. And I'm just sometimes looking on GitHub at some of the other projects, and I see them like things like, okay, it doesn't work, let's patch it. But that's another corner case, and you have the complexity. I think the most important thing that like in 2021 with proof of stake is dealing with complexity, because Satoshi Nakamoto's consensus is really simple, but the newer ones have totally different balance. They are really complex, and people sometimes, I think, are overly optimistic on how fast the things will start working. There will be probably years of turbulence, in a sense that people will find bugs and problems just because the systems are complex. So when people say, oh, we'll take proof of POW and move to proof of stake, sometimes I think people told me that people sometimes see me as a pessimist, but I'm actually been trying to just state something which is, you know, the newer systems are much more complex than the older ones, and that is ETH2 going to work as well as ETH1? I hope so. Truly, you know, but because it's much more complex, I think it will, for any complex system, the only thing which can help it is time. So I think if someone tells me, okay, will I personally move my money from ETH1 to ETH2? My answer would be, okay, probably I'll first move $10 and then I'll move $100, and I'll see how it works. So, and I think at some point people will understand that there's like lots of excitement about proof of stake, which is true, but I think there is a little bit of misunderstanding on that it will take time, and people, I think people will get there, and it's possible to do proof of stake blockchains, but people may sometimes underestimate how much time it will take to perfect, to polish all of these things.
All right, well, look, thank you for your talk today, Stan. I'm going to quickly share the screen of that last slide before we forget. Yeah, I can do it from here. I've got it, and then I can go present. And can people see my slide? Can anyone see my slide? Yep, I can see Sandra nodding. This is all good. All right, so we've had the talk from Stan, which was fantastic. So thank you again. Next week, on the 9th and the 10th, or 8th and the 9th, depending on which time zone you live in, there's the cross-chain workshop. We've got people from all over the world who are presenting. So that's going to be awesome. It's free registration. Go to the website and you can get on Eventbrite and get a ticket. In 2 weeks, Mikhail is going to talk about the ETH1, ETH2 merge and his thoughts on it. And then we're going to have a break at the end of March. And then we've got in April Tracer, which is a peer-to-peer finance platform. And so Isabel and Adam from Lion's Mane are going to talk about that. And then Raphael Belchior, I'm hopefully not mangling his name too much. He's going to talk about the state of blockchain interoperability. And Sandra, I've promised him that we'll have some hardcore cross-chain people on the call. And so given you've written one of the seminal papers, I'm expecting you're going to turn up. But anyway, so they're the talks we've got coming up, so they should be awesome. So thank you again, Stan, for coming on and giving the talk. Peter. It was great. So
thank you guys for listening.
Yeah. So yeah, anyway, so have a great day, everyone, and talk to you all later. Bye-bye.
You too, Peter. Bye.